So today we're going to take yet another look at circular motion. We actually already talked about it, so specifically we discussed uniform circular motion. So let's take a quick look at that and then see if we can expand on that. So hopefully you recall, if an object is moving around in a circle, so let's just say for kicks that the motion is counterclockwise. We talked about how velocity is always going to be tangent to the path at every point. Okay, so I'm going to call this V. I'll try to color coordinate things. So velocity is tangent to the path. Okay, and then we also said that U, as in uniform, refers to constant speed. Obviously, velocity cannot be constant because it's at every point of the circle pointing in a different direction. So speed is constant, velocity is not. We also talked about acceleration. So this one's a little off here. So acceleration vector always pointing towards the center of the circle, and it's always perpendicular to the velocity vector. And we call that centripetal acceleration. The word centripetal refers to something that's pointing towards the center. Okay, so this is all centripetal acceleration. So again, we can say that magnitude of centripetal acceleration, AC, is constant, but the vector itself, the way that we're used to writing vectors in terms of x and y, this is not constant. There is actually a way of writing it mathematically as a constant value, but that's beyond the scope of that class, so let's not worry about this. So we know the equation AC equals v squared over r. Obviously, r in this case is the radius of the circle, right? Obviously, that's constant as well. And if you're going to be checking units in this equation, units also need to be consistent with all the other quantities. So let's define a few more quantities. First of all, I'm going to define little omega. Don't call it W. This is a Greek letter, omega, little omega. And omega stands for angular speed or angular velocity. I'll call it angular speed because I'm not ready to talk about omega as a vector just yet. Okay, so angular speed. We'll talk more about rotational quantities in a couple of lectures. So for now, I'm just going to give you the basics here. The units are radians per second. Radians per second. Now, even though it's in radians, it does not mean that you need to put your calculator in radian mode. The only time that you need your calculator in radian mode if you're doing like a sine or a cosine or something like that of an angle measured in radians. You're not doing anything like that. The only place where you're going to be using angular speed is in relation to linear or tangential speed. So this is how you're going to define that relationship. So tangential speed V is equal to angular speed times radius. Now the units are a bit goofy here. So remember that omega is measured in radians per second, and radius is measured in meters. So a radian is actually a really funny unit. It's a unit when it's by itself, but when you multiply it by something, it's actually not a unit. So tangential speed, of course, is measured in meters per second, just like any other speed. So just keep that in mind. A lot of times in everyday English, everyday language, people would talk about RPM. So RPM stands for revolutions per minute. And I'm sure you know that term, revolutions per minute. You've heard that term RPM before. Okay, so that's kind of a colloquial everyday unit for angular speed. 1 revolution is 2 pi radians. That should also be familiar to you if you remember, like unit circle, how one circle could be 360 degrees or 2 pi radians. So you can convert from revolutions per minute to radians per second. That's just a simple unit conversion. So if you think about RPMs, you kind of already know what angular speed means. Another relationship, or another quantity rather, that comes in handy is capital T, which stands for period. So period is defined as time to complete one cycle. So this is a general definition, time to complete one cycle. So every time that something happens over time, every time that one cycle repeats, that's what we call period. Okay, so in this case, we can also say time to complete one revolution. Okay, it's time, so it's measured in seconds. And the relationship that involves period actually allows us to calculate what the speed is. So if you take the circumference of the circle, 2 pi r, and divide by the period, that's basically distance over time, right? So assuming that the speed v is constant for uniform circular motion, you're essentially just doing distance divided by time equals speed. So that's not a very complicated equation to understand. So that's how those two relate to each other. Another way to address uniform circular motion is in terms of little f, which is frequency. So frequency is the number of cycles, or revolutions in this case, per second. Okay, so the unit of frequency is called a hertz, capital H, little z. Hertz, named after an Austrian engineer, Hertz, who discovered radio waves. And the hertz is the same thing as 1 over second. Sometimes people even write it like this, s to the negative 1 power, as in reciprocal of seconds. Okay. So the relationship between frequency and period is f equals 1 over t, so those two are exact reciprocals of each other. You can also write big T is equal to 1 over f. So you're either talking about the number of revolutions per second or number of seconds per revolution. That's how those two are reciprocals. And finally, I'm going to give you one more equation here. Omega is equal to 2 pi f, or you can also write it as omega equals 2 pi over t. So you can compare all of these equations that I just wrote and see how they kind of all follow from each other. So it doesn't mean that I'm creating a lot of different equations here. I'm just kind of rewriting some of the previous one. And also let me rewrite the one for centripetal acceleration. Now that I've defined omega, I can also use omega squared times r to write centripetal acceleration. So this is just a bit more about motion. Obviously, a couple more useful definitions here that we haven't seen before, right? Angular speed, period, and frequency. Keep these quantities in mind because we're going to use them later down the line, even when we talk about oscillations, and even when we talk a little bit more about gravitation, which is coming soon. Okay, so there's useful quantities that we use to measure circular motion or measure some aspects of circular motion. And we'll do more on circular motion, or rather rotational motion, later. So the reason that we're talking about circular motion right now, it's actually not because of all of these quantities, speed, frequency, and all of that. It's because we also need to discuss forces. So we have this centripetal acceleration, right? That's our acceleration towards the center. Right? But now, after discussing forces for quite a bit, we also know that there is a relationship, Newton's second law, that describes how net force is related to acceleration. So I'm not going to box that because obviously we've boxed it enough times and we've discussed it enough times and we've used it enough times. But keep this in mind, right? So we're talking about acceleration here, and then we're kind of transferring the idea of Newton's second law to circular motion. Now, I have told you before that you shouldn't be writing F equals ma, just F equals ma. This is bad, because it's not every force that can be written in terms of mass times acceleration. It's only the net force, the sum of all forces. However, in this case, for the special kind of acceleration, centripetal acceleration, I can actually write centripetal force equals mass times centripetal acceleration. So this is a valid equation. And the reason for that is because centripetal force is actually not an additional force, not a separate kind of force, but it's actually the net force that's acting on the object if an object is going around a circle, or even part of the circle, like an arc. So let me write what I just said. So Fc is centripetal force. So again, remember, centripetal means towards the center. Right? So I can actually even go and make this a vector equation. Okay, so force, centripetal force points in the same direction as centripetal acceleration towards the center of the circle. In fact, let's go back to our picture here up front, and let's also draw direction of the centripetal force. Now, I'm not trying to create a free body diagram here. That's later. But I'm just pointing out that centripetal force and centripetal acceleration are both pointing towards the center of the circle, right? Hence the name centripetal. Okay, so the centripetal force is not a separate force, but a combination of forces that make the object travel around the circle. And again, it doesn't even have to be a complete circle. It could be a portion of a circle, like an arc, or just a turn, something like that. Okay? And when I say combination of forces, it really depends on the situation, but some examples would be normal force, gravitational force, this other gravitational force that I'm going to write as F with a capital G, and then we'll see what that means in a little bit. Force of friction, force of tension, and so on. So basically, there is no prescription of how this centripetal force is made. It really depends on the situation. It really depends on what other forces are present. I will show you a couple of examples in a few minutes. So here is another thought about centripetal force. This is a common point of mistakes, common point of confusion. So let's look at it this way. This is a road viewed from above, road that's making a turn, and here is view from above of a car. Here is the driver. So this car is traveling tangent to the circle. So here is the circle, right? So here is the path that this car would take. And at this point in time, right here, its velocity is tangent to the circle, right? So this is just a part of a bigger circle like this, okay? So what happens? Think about it as if you were in this car. You can be the driver or you can be the passenger. So the car is traveling in a straight line until it enters this curve, and then the car starts turning left. Think about it for a second. What does your body do? What does it feel like? So you probably are going to say something like, it feels like your body is thrown to the right. So if this is my circle here, this is maybe the center of the circle, okay? So it feels like you're being thrown outside of the circle to the right. So the car is turning to the left. It feels like your body is leaning to the right. So you probably have heard the term centrifuge or centrifugal force. So don't confuse the two. Centripetal and centrifugal. The word centrifugal means away from the center. So the word centrifuge means a device where centrifugal force is acting. For example, centrifuges are used in medicine to separate the layers of blood. So if you put blood or any other bodily fluid into a test tube and you stick it into the centrifuge and you run that centrifuge machine, it separates the layers of blood. Okay, cool. All of that is interesting and nice, except one thing. This force doesn't really exist. This is a fake force. So the word centrifuge is actually a misnomer. Centrifugal force doesn't exist. Here is why. We know that no matter what kind of forces we're talking about, forces are always exerted by something, right? By an external agent of some kind. So imagine yourself sitting in the car. So you're sitting in the car seat, your feet are on the floor or maybe on the gas pedal, right? You're holding onto the steering wheel. You're wearing a seat belt because you're always supposed to wear a seat belt, right? So all of that is going on. So all of those objects that are touching your body, they are still touching your body in exactly the same way as the car is turning. So there is absolutely nothing new or nothing else that adds up to the system when the car is turning. There is no new agent when the car is turning. So there is a new force, and yet there is nothing that could potentially perhaps exert that force, right? So that kind of doesn't work. So that's why centrifugal force is fake. It's something that people who didn't quite understand physics invented in order to explain what's really happening. So centrifugal force doesn't exist. So what is it that you're feeling? Think about Newton's first law for a second. Think about the car turning. And think about your body wanting to go in a straight line. So what's really going on here is that the car is turning left while your body, being a separate object, wants to continue in a straight line according to Newton's first law. So remember that Newton's first law is law of inertia. So the inertia of your body wants to continue moving in a straight line. So the car is turning away from underneath you, and it takes some short amount of time for your body to catch up to the motion of that car. So really, there is a centripetal force. right? So the car is exerting centripetal force on you because your body motion does catch up to the motion of the car. It's not like you're, flying through the window and leaving. Good thing too that you're not. So the car turns. It does take a little short time for your body to catch up to the car, but the car is what's exerting centripetal force. So there is nothing unusual about that. You're already attached to the car. You're already touching it. But centrifugal force would be quote unquote new, and there is nothing new that comes into play when the car is turning. So just think about that all the time. So this circular motion and this quote unquote centrifugal force that you're feeling is not a force. It's an illustration of inertia, illustration of Newton's first law. Okay. So let's look at a couple of examples where we can set up an equation to solve for centripetal force or to see what other forces are contributing to it. Let's start with, I'm going to do horizontal circle that an object makes, so like a ball tied to a string, okay, and it's making this horizontal circle. Okay, so imagine this is completely flat. Okay, so here, if you're going to draw forces, there is a force of gravity, obviously, but that's perpendicular to the plane of motion, so that's not even gonna matter. Okay, so maybe I won't even draw that. And then you have this force of tension exerted by the string. So again, I'm going to ignore force of gravity because it's perpendicular to the motion. And I'm going to say that net force equals mass times centripetal acceleration. Because here is your center of the circle, right? So we know centripetal acceleration points towards the center. So in this case, it's only the force of tension that contributes to centripetal force. In other words, force of tension is the centripetal force in this case. So it's not a new force. You're never going to put centripetal force on your free body diagram. Now, this is, strictly speaking, is not a free body diagram, right? It's just an illustration, but whatever. Okay. And you can also do the same thing, like if you tie a string to a ball and you make the ball go in a horizontal circle, but the string is kind of at an angle, right? So there is still going to be centripetal force towards the center. And here I am going to draw force of gravity and force of tension like this. Okay. Now what I would do here is to break up the force of tension into horizontal component and vertical component. Right, so this is Ftx, Fty, and maybe you can define that as theta, right? So then you could do exactly the same thing as what we always do. You can write sum of all forces in the x direction is equal to mass times centripetal acceleration, and sum of all forces in the y direction is 0. Right, so here I have Ftx equals to mass times centripetal acceleration, and I have Fty minus Fg equals 0, right? So the second equation here is not essential. Now it's only a component of force of tension that contributes to the centripetal force. That is the centripetal force. Let's do another example. This time it's going to be a vertical circle. So imagine maybe like a track of some kind, vertical track, and there is a little car, toy car, moving in the vertical track like this around the circle. Okay, so like one of those Hot Wheels loop-de-loop things, right? So at the top I can draw a free body diagram. Here at the top, if the cart is moving on the inside of the track, I would have force of gravity, and I would have a normal force, right? So the track, it's not really support force, not much of support there, but the track is obviously in contact with the cart, so it exerts a normal force. So here, I would write sum of all forces in the y direction equals to, guess what? Centripetal, mass times centripetal acceleration, right? And I'm gonna make downward direction as positive because that's what I always do. So this is equal to mass times centripetal acceleration. So I have Fg plus Fn equals MAC. So this combination of forces is, I should keep it color coordinated. This combination of forces is what makes up centripetal force. I can do the same thing on the bottom here. I'll draw this new free body diagram. So there is the same force of gravity, right? But now normal force is upward, and it has to be larger than the force of gravity to provide this upward acceleration. And you should be able to go through all of this really quickly now because we've done a lot of pictures like this by now, right? So again, I'm going to write sum of all forces is equal to mass times centripetal acceleration. This time I will write it as Fn minus Fg equals mass times centripetal acceleration, right? So this is the combination of forces that gives us centripetal force. Okay? So notice that even within the same setup, even within the same motion, centripetal force doesn't have to stay written in terms of the same combination of forces. So it really depends on what's happening. And if the cart was outside of the track, like this, then there definitely would be a different combination of forces, right? So again, here we have gravitational force and normal force. One more example. This one is called banked turn. Banked turn. So imagine if you ever watch NASCAR races or bike races or motorcycle races, if you notice, all the turns are not flat. All the turns are banked a little bit, right, at an angle. Even forget the races, even some of the off-ramps and on-ramps on freeways, typically off-ramps, are banked a little bit. So there is an angle. Now, this is not the same thing as inclined plane. There is just no better way of drawing it. So this is how I'm going to try to draw it. So imagine this is like part of the road, but it's banked at an angle theta. So here is a car as viewed from behind that's making that turn. I know this is a really awkward picture. It's kind of hard to draw and it's hard to visualize. Just think of a turn that's angled, banked. Okay? So here, the center of that turn is over here, right? So there is the centripetal acceleration. This is not a complete free body diagram, but I'm just going to leave it at that. So there is going to be a gravitational force and a normal force. There could also be a force of friction, and I encourage you to go through this idea of a banked turn one more time by yourself with friction included, but I'm going to set this up to deal with it without friction. And there is an actual real reason why I want to do it without friction. It's not only because I'm simplifying math, and I'll get to that reason in a minute. So because this is not inclined plane, I am actually going to keep my axes, X and Y, in the standard orientation. Okay, so X is horizontal, Y is vertical. And what I'm doing here is I'm lining up the x-axis with the acceleration, because I don't want to deal with two-dimensional acceleration. So this time what I'm going to do is I'm going to break up the normal force into two components, x and y, like this. Okay? And let me write this. So F and X, if this is angle theta, then this is also theta. Nope, not that. Oh, I just did not label it correctly. Okay, so this is going to be angle theta. All right, so Fnx is going to be Fn sine theta. Fny is Fn cosine theta. The proof of that is very similar to the inclined plane. What I'm not doing here is I'm not lining up the coordinate axes to the plane itself. So I have acceleration in the x direction, and that's specifically centripetal acceleration. In the y direction, nothing is happening, right? So the car is not jumping up and down or falling through the surface, nothing of that sort. So for the x direction, I only have F and X contribution, right? So here, this is my centripetal force. So a component of a normal force can also play a role of centripetal force, okay? I'm actually going to take this one a couple of steps further, because remember I said there is a practical reason why I'm showing this to you, not just math. Okay, so let's take it a couple of steps further. For the y direction, I'm going to write Fny minus Fg equals 0. So Fny equals Fg. Fn cosine theta equals mg. Again, I'm going through this fairly quickly because we've done this force stuff before, and we've done even much more complicated stuff than this. So I'm going to solve for Fn. Okay. And then I'm going to go back to my x component, right? So this is going to be Fn sine theta equals m times centripetal acceleration. And I'm going to substitute this expression into Fn. Just bear with me for a minute. mg over cosine theta times sine theta equals m times centripetal acceleration. Cancel the m's. Remember that sine over cosine is tangent. So this is g tangent theta. And on the right side, I'm going to substitute the definition of centripetal acceleration, v squared over r. So obviously r is the radius of the circle. Okay? So my goal here is to solve for this answer. V equals square root of r g tan theta. Now, I'm not going to box it because, again, it's not a formula that I need you to know. It's a result of this particular example, this particular setup. But this is exactly why I'm saying that this has a practical reason. So if you remember going around an off-ramp where the curve is banked at a little angle, and maybe there is a posted sign, usually in yellow, that says speed limit is 15 miles per hour. Not like an actual limit, but kind of a suggested limit. So where does that come from? It actually comes from this equation. So that posted suggested speed limit comes from geometric considerations. And we're taking that to be without friction because that suggested speed limit should be a safe speed to drive in any road conditions, even if it's icy, even if it's wet, even if it's windy, even if there is whatever stuff on the road. So that speed limit is based on geometry, as in the radius of the turn and the banking angle. Okay? Now, in reality, it's a bit more complicated than that. So even though this equation is independent of mass, but it's still a bit oversimplified. Okay? So engineers usually have this idea that's called a safety factor. I'm not going to ask you about this on an exam, but basically safety factor is like an extra factor to be safe. So for example, if you take this speed and you calculate the safe speed to be 30 miles per hour, engineering safety factor of 2 would tell us to post the speed limit of 15 miles per hour. So this is just like just in case. So this obviously doesn't take into consideration the shape of the car. So for example, big trailers, big trucks, semi-trailers, they have a very high center of mass. We haven't talked about center of mass yet, but we will. So for them, it's actually where that force of gravity is acting is actually a little bit different. So there is other considerations that come out of that. But that posted safe speed limit, it's safe even for them. So even in the absence of friction. And of course, if this car, so now I'm looking from above, if this car was sliding without friction, it would slide out of the turn, not into the turn, right? So if it's moving out of the turn, there is, in regular conditions, force of friction contributes to the centripetal force. It's easier to stay within that turn if there is force of friction. So if it's really wet and ugly on the road, you should not be exceeding that speed limit. But if it's dry, you shouldn't be exceeding it anyway, but it's much easier to stay in turn even if you're going a little bit faster than that posted speed limit. Don't try that at home, but I'm just saying that friction would also help to contribute to centripetal force. And like I said, I recommend that you take the setup, add force of friction to it, right? So into the turn, but it's going to have to be along the plane, obviously, right? Because that's where the contact between the wheels and the road is. And see if you can redo this analysis with force of friction. So anyway, as far as centripetal force is concerned, as far as uniform circular motion is concerned, now you also have a way of addressing uniform circular motion in terms of forces.